Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 9, Organic Chemistry 3. Carbohydrates and nucleic acids. Carbohydrates. Carbohydrates are the most abundant organic compounds in nature. Nearly all plants and animals synthesize and metabolize carbohydrates using them to store energy and deliver it to their cells. As this name implies, the most common sugar have molecular formula that fit hydrate of carbon pattern. That is CM, CN, H2O, M. For example, sucrose, table sugar, has the formula C12, H2O11, or C12, H22O11. Glucose and fructose, sugar prevalent in honey, have the formula C6, H2O6, or C6H12O6. Plants synthesize the carbohydrate in a complex series of reactions using sunlight as the energy source to convert carbon dioxide and water into glucose and oxygen. Many molecules of sugar, glucose, can be linked together to form either starch for energy storage or cellulose to support the plant. Classification and properties of carbohydrate. As a result of more modern understanding of their structures, carbohydrates are now defined as aldehydes and ketones containing a number of hydroxy groups on an unbranched carbon chain, as well as their chemical derivatives. A carbohydrate with an aldehyde carbonyl group is called aldose. A carbohydrate with ketone carbonyl group is called ketose. Carbohydrates can also be classified by the number of carbon atoms they contain. A 6-carbon carbohydrate is called hexose, and 5-carbon carbohydrate is called pentose. These two classifications can be combined. An aldose with 6 carbon can call aldohexose, and a ketone is a ketone, ketopentose is a ketose containing 5 carbon atoms. A ketose can also be indicated by the suffix ulose. Thus, a 5-carbon ketose is called pentulose. Well, another type of classification scheme is based on the hydrolysis of certain carbohydrates to similar carbohydrates. For example, monosaccharides cannot be converted into similar carbohydrate by hydrolysis, like glucose and fructose. Well, disaccharides can be converted by hydrolysis into 2 monosaccharides. Trisaccharides can be hydrolyzed to 3 monosaccharides. Oligosaccharides can be hydrolyzed to a few monosaccharides. And polysaccharides can be hydrolyzed to a very large number of monosaccharides. Before we get into the carbohydrate structure and reactivity of this species, we would like to recall Fischer projection. The Fischer projection is based on an eclipsed molecular conformation. Keep that in mind, okay? So the first step to draw the Fischer projection is to arrange the molecule so that the chiral carbons and the largest continuous chain are in vertical line. The aldehyde groups representing carbon 1 goes at the top. Draw the horizontal lines to make cross C2, C3, etc. So we have here 2 and we have here vertical cross line. Step 3, put the OH on the exact side of the cross. So we have here the OH right hand, then the OH in Fischer will be on the right hand. Then remove the carbon and keep that solid. Okay? Now if I look for the molecule here I present, I have the aldehyde and CH2 from my side. Remember, that's from my side. It's in the back. Okay? And the OH will be on my right hand and the H on the left hand. So aldehyde on the top. Okay, this is aldehyde. From my side, this OH is on the right. H on the left. And the long chain going up and down here, that's the CH2OH, will be in the back. You have OH and the H in front, and the aldehyde and the CH2OH are in the back. Let us try to draw this molecule in a Fischer projection. Okay? Well, here it is. Remember that you are seeing the mirror of it, okay, on the screen. But to me, this is what I have: the aldehyde in the back, then this is carbon 2, the OH is on the right, H on the left. I will put the molecule in the eclipsed form, so I have to rotate. Okay, now I have C2 and C3 in the eclipsed form. The OH now on the right, the H on the left, and CH2 in the back. I have the molecule now in the eclipsed form. So the aldehyde in the back, here is vertical, carbon 2, 3, and CH2 in the back. Now OH right, and on 3 right. That's the Fischer projection of this species. Remember, you are seeing the mirror of it. Let us try to draw this molecule in a Fischer projection. Well, as we mentioned, we have to have the aldehyde in the back, C2, C3, C4, again we have to put that in eclipsed form, C4, C5, okay, and here is the terminal, C6. So now the molecule is folded. We fold the molecule to have the 2 and 3 and 4 and 5 in eclipsed form. Now, as you see here, aldehyde in the back, so it will be on the top. OH on carbon 2 right, on 3 left, on 4 right, 5 right. So this is Fischer projection of this molecule. You release it. So We take it from the 3-dimension to rotate until we get eclipsed forms, and then we draw the structure of Fischer projection. Right, left, right, right. Aldehyde in the back and a CH2OH in the back. Redraw the hashed wedge line structure of sugar A as a figure projection. Here is sugar A. I build a molecule model. Here we are. We have aldehyde. We have the OH in the back. We have the OH in the back. From my point of view, of course, okay? Once again, remember you are seeing the mirror, okay? And here in front, OH. And here is a CH2OH terminal. We have to rotate the molecule until we get the aldehyde in the back and all C2, C3, C4 will be in eclipsed form. Okay, now here is the aldehyde in the back, here is C2, here is C3, here is C4, and this is a CH2OH. So the molecule will be on that conformation to draw Fischer. We have the aldehyde. On carbon 2 OH left, on carbon 3 OH is right, 4 OH is right, and the CH2 in the back. Here this in the back, right? To derive the 3-dimensional model of a molecule from its Fischer projection, just reverse the process. Here we have the Fischer projection. All what we have to do is put this OH up and this H up, and the aldehyde will be in the back. Okay. Then this is vertical line. Then the CH2OH will be in the back. Here we have it in here. The aldehyde in the back. The OH in the right, OH in the right, and then CH2OH. If I put the molecule this way, so the OH will be up, up the plane, OH up the plane, the two H's are in the back, okay? The aldehyde and the CH2 will be on the plane. Let us recall some rules for manipulation of Fischer projection. Fischer projection may be turned 180 in plane of paper. Here the vertical line, aldehyde on the top, CH2 at the bottom. Rotate in plane of paper 180. You get the aldehyde down, CH2 up, and the OH from the right to left. No change on the configuration of the asymmetric center, and that's allowed. A Fischer projection may not be turned 90 in the plane of page, so rotating the molecule 90 degrees, that's forbidden. Why? This manipulation violates the Fischer project convention that all asymmetric carbons should be aligned vertically, so that is forbidden. A Fischer projection may not be lifted from the plane of the paper and turned over, So if we move the molecule around the X here, rotated, okay, 180, the OH will be, OH here, right will be on the left, right will be on the left, and we get a mirror image of the starting. So they are enantiomer. So the rotation will let the OH leave the plane of the screen, right? Once it moves out of the plane, it's forbidden. Okay? Rule 4, the three groups at either end of a Fischer may be interchanged in a cyclic permutation. Here we have a symmetric center. We have group 1, 2, 3. Yes, we can rotate H, replace OH. OH replaces the CH2OH, and the CH2OH replaces the H. So H will be here, OH will be here, and CH2 will be here. That's allowed. Okay? As if we have two successive change. H replaces OH, and then the CH2OH and OH interchange. Okay? This rotation allowed like two successive two-group exchange. An interchange, that's what we're coming to it, an interchange of two of the groups bound to an asymmetric carbon change the configuration of that carbon. So if we change H replaces the OH, okay, we get the enantiomer. Again, if we change OH to the C with CH2OH, another one, then we get the same as starting. Same molecule, same configuration around this carbon. The RS system can be applied to Fischer projection. Well, what we have to arrange the priority of the group around the chiral center, put the lowest priority 4 in the back on the top here, and then arrange the others. If we come 1, 2, 3 clockwise, then the configuration is R. If we get 1, 2, 3 anti-clockwise, then the configuration is S. As an example, assign the R and S configuration of this chiral center. This chiral center has four groups, hydrogen, OH, aldehyde, and CHOH, CH2OH. According to the priority, 4 is the lowest, OH is number 1, the highest, then aldehyde, and then this group. So we have around the chiral center, we have 1, 2, 3, and 4. Well, as we mentioned, if we do two excessive change here, 1 and 4 and 2, 4 and 2, and then change 1 and 2, we will come up to the same configuration as a starting. They are the same. 4 in the back, here 1, 2, 3, so we are getting clockwise from 1 to 2, 2 to 3, so the configuration is R. This is R. See you next lecture.